All right, everyone. We are now going to talk about ray tracing on mobile with Iago Calvo Lista at ARM. Please give them a warm round of welcome.
Well, hello. Welcome to my talk, Realistic Graphics with Ray Tracing on Mobile. My name is Iago Calvo Lista. I work as a graphics software engineer at ARM. Okay. During this talk, we will explain you how you can use Vulkan to add and optimize ray tracing effects to your games. We'll start with a quick introduction to ray tracing and continue with some advanced effects like transparency and skin animations. We'll continue with optimization techniques like combining screen space and query effects, and how you can use variable rate setting to increase the frame rate of your ray tracing effects. We'll finish with some conclusions about how you can use ray tracing. During this talk, most of our suggestions will be focused on ARM, Mali, and ARM Immortalis mobile GPUs, but most of our suggestions will apply to other mobile GPUs and to all GPUs in general. Okay, some of you may remember that we already gave a similar talk last year in Vulkanised. However, at that time, mobiles with ray tracing were pretty new in the market, so we didn't have time to investigate a lot. We only implemented very basic effects, and we didn't have a lot of suggestions and optimizations. This year, things look very different. There's multiple vendors with hardware with dedicated hardware for ray tracing on mobile. And we had a lot of more time to investigate and show you some suggestions and optimizations. And now we can reach more than adequate performance on actual mobile devices in the market. First, I would like to start with a quick reminder about how ray tracing works. I would like to suggest everyone who is interested in the basic details to review our last year presentation for more information. What exactly is ray tracing? Ray tracing is an API for ray intersection test. The API allows the user to define a ray origin and a ray direction, and test it against the scene geometry. The default behavior of the API is to return the closest hit that the ray will intercept in the scene. Vulkan ray tracing API is very flexible. It allows for some creative uses. For example, you can use ray tracing to simulate vertical collisions in a physical simulation. However, the main use case for ray tracing, and the one that we will focus during this presentation, is rendering. Ray tracing allows our applications and games to simulate the behavior of the light in a way that closely resembles the physical reality, simplifying a lot of for development. So how does ray tracing work on Vulkan? Vulkan uses the same API for ray tracing in both desktop and mobile, so I expect a lot of you to be already familiar. First, we have accelerating structures, an optimized data structure containing geometry data for fast intersection test. Accelerating structure can be divided in bottom-level accelerating structure, or plus, containing the actual geometry, and top-level accelerating structures, or TILAs, containing other plus. For ray traversal, Vulkan offers two options. First, we have ray query, the way that we're recommending for implemented ray tracing on mobile. Ray query allows us to launch rays in length from our existing shaders. Then we also have ray tracing pipeline. Ray tracing pipeline offers some new shader states that we can use to control ray tracing. This is a more driver managed approach, so there's a lot of more magic. We also have descriptor indexing. Descriptor indexing or bindless resource is technically not necessary for ray tracing. However, we greatly recommend using it. It's pretty standard. It's a core feature of Vulkan's version 1.2, and it allows us to retrieve the material information for hit objects in a very easy and efficient way. For this presentation, we will use our internal ray tracing demo that I haven't showed you all of you in their booth, and that I can show you later if you're more interested. We're using physically based rendering materials because they're very easy to integrate with ray tracing, as I will explain later. We have a hybrid rendering. We will have a different G buffer. We will have a G buffer computed using a raster device. This is illuminated using a classic deferred illumination. Each one of ray tracing effects is implemented as a different post process that will read from the G buffer to launch the rays. We are using one render pass per effect. This is not the most optimal way in terms of bandwidth. It would be better to try to combine them all together. But we had a lot of, we will make this demo with not so much performance, but more like experimentation and quickly develop. Here we have the thing that we will use for most of our presentation without ray tracing effects. And here we have, once we are adding the different ray tracing effects, you can clearly see how much the thing changes between both options. In this option, we're showing the number of hits that we're hitting in ray tracing shadows. You can see how most of our kits are in transparent objects. Here we have some basic information about the scene that we are rendering. We will use this information for all of our scene. You can see how we are rendering 1.6 million triangles, which we consider to be relatively representative. And here, it's finally some performance data obtained on a Vivo X100. This is powered by an ARC Immortalis G720, and it's a device widely available in the market, and with more than enough performance. Here we have the performance of different effects. This will vary a lot depending on your content, and also about the camera angle. But the most important thing is that we are reaching 80 frames per second. And in this thing, we are tracing an average of two ray tracing rays per pixel. We're launching 1 per shadows, 1 per reflections, and 4 for refractions. So all average to around 2 rays per pixel. Now, I will present some more complicated effects that you need to implement if you're using ray tracing, and some suggestions about how to do it. First, I would like to start with ray queries with transparency and shadows using alpha textures. Here, we can see how what alpha textures can add to your scene. You can see how the shadows will change completely for the tree in the floor, and also how the reflections look a lot better with the proper transparency. To implement this effect, transparencies, we will need to read the alpha textures during ray traversal. This is not problematic on desktop, but on a tile architecture, this is very problematic, since we will need to access endless resources. This will greatly increase memory bandwidth, so one should only use transparency when they are really necessary. When using ray query receipt will return files once it has a confirmed hit. For non-opaque materials, we will need to access bandless resources, read the alpha textures, and check the value to confirm if the hit is valid or transparent. For ray tracing pipeline, we have to do something similar, but in the any hit cider. We will just access bandless resources, the alpha texture, and confirm or ignore the hit. A Vulkan API has different flags to mark opaque materials as opaque. This is very important and can greatly increase your performance, and we will skip invoking the hit cider and the ray query internal loop. Finally, this year we also added skin animators to our demo. Skin animators will request to update the bottom level accelerator structure. This is really expensive, so we recommend to try to minimize the number of skin miss in your scene. We also recommend trying to distribute the update of the bottom level accelerator structure across multiple frames. You don't need to update all the bottom level accelerators all the frames. You can have some kind of heuristic. Also, for bottom level accelerator structures that are really far from the camera, you can implement some heuristic to not update them or reduce the update. This is very tricky since reflectance and shadows will interact with objects that are no longer in the first frame. When building an accelerator structure, we have two flags that we can use, fast trace or fast build. We recommend to use fast trace only for static geometry and use fast build for dynamic geometry. The difference on desktop is not so relevant, but on mobile and Intel GPUs, fast build is a lot faster to build. So that's our recommended suggestions. Also, when building a new accelerator structure is a lot slower than updating or refitting an existing one. So we recommend that if it's possible to specify the source of a previous accelerator structure to use as a base. This will greatly increase your performance. And also, it's not so much related with the skin animators, but please consider to inspect your bottom level accelerator structures. Try to reduce empty space and be sure that there's not a lot of overlap. That can greatly increase your performance. Now, I want to show you how you can reduce the number of rays that you are using in your ray tracing effects by using a technique called hybrid ray tracing. First, let's start with a quick overview of how we do ray trace reflections. First, we retrieve some information from our G buffer, like the normal, the depth to compute the position, and things like that. We also retrieve some physical-based data, and we use the roughness to compute the number of rays. Mirror reflections with a very low roughness need only one ray. However, if we want glossy reflectance, we will like to launch multiple rays and use some kind of a stochastic average. When we have the set of rays, we just generate some data and we trace arrays using either ray query or ray tracing pipeline. If a ray hits some object, we just need to retrieve material information using bandless resources and illuminate the hit. If a ray fails and it doesn't hit anything, we just sample an environment map to reflect the sky. It could be possible to implement recursion and have multiple bumps of the light. if we are hitting one reflective material, we just have all the information to launch an extra array to implement recursive reflectance. It's recommended to try to minimize the number of ray tracing arrays that we are launching in our SIEM. So with that in mind, I would like to have a quick overview of screen space reflectance. Screen space reflectance is a popular ray merging technique. So I will just give a quick overview of how the algorithm works. It can be adapted to work well with a physical and a stochastic approach. So it was very easy to adapt to our demo. We start by transforming the ray origin and ray direction from wall space to screen space. We interpolate this ray for each pixel, and we check the depth of the ray in each pixel that it's visiting. In this pixel, we have different options. First, the interpolated ray can be very close to the depth in the G buffer. That means that we're hitting some object, and we can just reflect it. If the depth of a ray is above the current value in the depth buffer, we are traversing empty space. So we just need to continue iterating. There's also the option that the ray is below the depth buffer. It's not so clear how to handle this. For a demo, we handle to choose this situation as a fail and consider the screen space reflecting ray is failing. This could be an important demo, but it's not so clear. But there's multiple options to handle this ray. Screen space reflectance can be easily integrated into a physically based render, so they are good fallback with the base lacking ray tracing support. They have lower quality than ray tracing reflectance. They are faster and handle transparency correctly. But they struggle a lot with objects that they are no longer in the screen. They are also a lot more complicated to implement than ray tracing effects. To obtain good performance and good quality from a screen space reflecting approach, you need a lot of magic numbers. So ray tracing could greatly help you to improve that. As I said, screen space reflectance are a very popular method. So there's a lot of different optimizations and a lot of easily available information that you can check. I will greatly encourage everyone to consider using a hierarchical approach, where we compute a hierarchical bit map of the depth value to increase your traversal through empty space. Some desktop games are trying to use screen space techniques and combine them with ray tracing effects. In our demo, we have a screen space and ray query reflectance, so we also look about how to combine them. The initial idea was to first launch a screen space ray, and only launch a ray tracing ray if this ray query ray fails, if this screen space ray fails. If the screen space ray hits something, we can skip bytelets, since we have all the necessary information to illuminate the ray already in the G buffer. This is very important in Atlas architectures, and accessing bytelets is really costly, so we want to avoid that. However, when sampling the G buffer for a screen space reflectance, the common approach is to directly sample the illuminated result. The illuminated result in the G buffer, it's illuminated with respect to the camera, not the direction of the reflected ray. So it has a wrong incident direction. This can cause some artifacts when combining with ray query that we're illuminating with the proper reflected ray direction. This is almost unnoticeable, and it's very difficult to notice, but we decided to add to our G buffer all the material information to be able to compute the illuminated color using the correct ray direction. Also, when implemented reflectance, it's very easy to have a lot of spilling. This is usually because we're copying data that we are using. I greatly suggest all of you to profile very frequently, and I recommend using the Mali offline compilers, and it's really helpful to detect this situation where we have when we have a lot of spilling due to copy data that we don't want. A pretty common problem in hybrid renderers that are using the raster pass to launch rays from the G buffer, it's how to avoid self intersection. There's different popular solutions. One of the most fun is to use ray flags like cooling, not front-facing triangles. However, this cool flag will require extra GPU work. Another option is to increase the T- of the ray or some bias to the ray origin to skip all the close self-intersecting objects. However, this is also not ideal, and it's very easy to create some bugs. Instead, we propose to use a screen space ray. In reflectance, we are always launching a screen space ray, and we know that we cannot intersect anything until this screen space reflection ray is failing. So we can launch a ray query ray from the last pixel that is visited by screen space reflection. We just need to transfer from screen space to wall space to launch the ray query ray. This will greatly depend on the performance that you can gain from this can greatly depend on your content. but we found that it's really useful for objects with a really detailed geometry or with objects with transparency, since most of the self-intersections will occur in the closed pixels. As I said, glossy reflectance is roughness to control the ray direction. This can cause a huge ray divergency in the direction of the ray. When doing ray tracing, ideally we want all our rays in a warp to follow a similar path to the accelerating structure to have better memory bandwidth. And we also want to avoid a single ray that follows a divergence path to slow the entire warp. This can also happen in a pure mirror reflective environment, but according to our experience, this is a lot less relevant. We have trained using several operators to check the GPU occupancy. In screen space, we can terminate warps with a low occupancy in each one of the screen space reflectance iterations. Similarly, before launching a recovery ray, we just check the occupancy of a warp to avoid warps with very low occupancy. And finally, I would like to show you some images about how much reflectance can add to your scene. Here we have the scene without reflectance. And here we have a screen space reflectance. Our implementation of screen space reflection is not ideal. It could be greatly improved if we wanted to be less precise. But you can still see how there's reflecting some objects in the scene, but most of the thing is from the environment map from the sky. Here we have ray reflectance. You can see how much ray reflectance add to the scene and how much better quality they have compared to the screen space reflecting. And finally, we have hybrid reflectance. You can see how hybrid reflectance have identical visual quality with ray reflectance. And finally, just to give you an idea, in this image, we're showing which part of the scene are illuminated by screen space reflectance, which ones are illuminated by ray reflectance, and which are ray mist. So we're just illuminating the sky sampling from environment map. And here we have some quick performance about how much you can get using an hybrid technique. You can see how screen space reflection is the faster approach, but as I said, the quality is not really comparable, so it's not really significant. Ray is a lot more expensive, but it can still offer more than adequate performance. An hybrid approach has a slightly overhead, but just adding some of the small optimizations that I mentioned can greatly increase performance. And finally, I would like to avoid continuing with shadows. Our shadows are very similar to our reflectance. We first sample from the deep buffer to retrieve some information. Then we generate some days using mostly physical-based rendering data. And then we launch a hit using either ray query or ray tracing pipeline. If this ray hits something, it means that we are in shadow. If it reaches the light, it means that we are not in shadow, so we can illuminate the pixel. We have two important optimizations in our shadow pipeline. First, we are avoiding launching a lot of unnecessary lights by checking if the light is behind. If you use the dot product between the normal and the light direction, you can check if the light is behind the object and you can skip launching the rays for those objects. Also, for shadows, we technically don't need to know which objects we are hitting. We just need to know if we are hitting something. In reflectors, we need the closest hit, the actual thing that we're hitting, to be able to retrieve the bindless materials. This is not the case for shadows. We can use just ray flags to terminate on the first hit instead of the closest hit. Here we can see how much shadows are adding to their scene. Most of the performance gain of hybrid reflectance came from skipping bindless for illuminating. However, in our internal tested, bindless reflecting also shows to be a bit faster to traverse through the accelerating structures, as we can skip a few ray tracing rays. And our shadows follow a similar algorithm to our reflectance, so we thought that we can also implement hybrid shadows to check. Here we have the shadows that we can calculate without launching any rays. These are shadows that we can compute just using the dot product to check that they are not facing the camera. This will greatly depend on your scene, but they can add a lot of shadows and save a lot of performance. Here they're using screen space shadows. Screen space shadows add just a bit of detail, but there's not a lot of things they add. Their main performance gain is that they allow us to skip most of the close intersections when using an hybrid method. And here we have proper ray shadows. You can see how they add a lot of details, especially in the shadow of the tree. And here we have hybrid shadows. The visual quality between ray shadows and hybrid shadows is almost identical. In hybrid shadows, we have a lot more shadows in the tree because we can have a lower threshold to detect a self-intersection test. And finally, we have some performance about ray query and hybrid shadows. Screen space shadows are obviously the faster, but they have the lower quality, so they are not really comparable. When using ray query, we have a similar performance, so it's what we recommend. This is mostly because ray query can save you a lot of memory bandwidth. When we are using an hybrid technique, we have a slight overhead. Using an hybrid technique with all of the optimization is slightly faster, but it's basically the same performance. But as I said, in an hybrid technique, we can have a lower threshold, so we can add a lot of extra shadows that we are not detecting if we are just using ray query. Now, I would like to speak about a bit variable rate shading and how it can be combined with ray tracing. Variable rate shading is a Vulkan extension that allows us to render some elements of an image at a lower resolution. It allows us to concentrate fragment density in the part of the scene where it is actually needed. Vulkan has a flexible API for this. We can set a fragment rate per draw call, per primitive, or using a shaded attachment image. That is the most flexible way. We also have the option to combine multiple methods at the same time, and different options about how to combine them. Variable rate shading is a very interesting topic, and I will suggest everyone who is relatively interested to visit last year's presentation to learn more about how to use it in different effects. Vulkan allows us to combine ray tracing effects with variable rate shading. There's different ways to use it, but our recommended ways to use a screen space shading attachments and define something of a heuristic. We just use a compute pass to set the appropriate density rate for each pixel in the image. This is very flexible. However, finding the heuristic might be complicated and it's not completely clear. For example, it's possible to just use the luminance to render darker areas where data are not so noticeable at a lower resolution. This could be really helpful for ray query reflections. For demo, we have focused on shadows. We assume that a shadow area will remain relatively constant between two frames. So our idea was to use the previous frame and concentrate shading power at the shadow edge. This can cause flickering, but if you have a good enough margin, you can avoid it completely, and you can have a huge performance quality. Here, we have different performance data about rendering shadows at different resolutions. When we're rendering shadows at full resolution, it's a lot more expensive. And rendering a half resolution, it's faster. This is pretty obvious. Variable rate shading is in a midpoint. However, I want to insist that variable rate shading has the same visual quality as a full ray shadow approach. So it allows us to gain a lot of performance without sacrificing quality. Now, to end this presentation, I would like to remind you some of the advantages of ray tracing. Ray tracing can provide a huge quality uplift to your games, and it's very easy to implement complex effects. Ray tracing, it's very close to reality, so implementing things like reflections or refractions, it's easy. You don't have magic numbers. You can save a lot of work debugging the screen space effects and similar things. The Vulkan API for ray tracing is the same in desktop and mobile. It makes it very easy to export your game and effects from your desktop games to your mobile games. So we recommend you to try. It's also a very flexible API, so it's very easy to implement optimizations and to add some kind of customization to make your effects more differentiable. And finally, I would like to reiterate the last presentation invitation to join our undeveloper program. We have a lot of information there, and members can ask us frequent questions in our Discord on different methods. We also have a lot of learning paths coming about ray tracing, including some more information about how this demo was made and more suggestions. And now I would like to thank you and wait for any questions.
Could you go back to the slide about alpha transparency for a minute? I have a question. Is ARM looking into possibly supporting something or implementing something similar to the opacity micromap extension?
I cannot answer that question.
Okay.
Legally speaking.
Okay. Okay, but you are aware of the opacity micromap, right?
We are aware of multiple extensions. But
okay.
Please don't make my life hard.
I'm not that familiar with ray tracing hybrid methods, but why is it you get self-intersections with the G-buffer when you're...
Well, the idea is that in the G-buffer with compute, you have the depth. Use the depth to retrieve the position. And retracing is very precise, so if you have some kind of inexactitude, you, instead of launching the depth from the exact position of the geometry, you're launching it a bit close. This is close enough for most effects, but in ray tracing, you can actually hit the triangle in your same position. You instead of you're launching like a bit behind the actual triangle, mostly to precision problems.
All right, one more round of applause.